Greetings, this is Derek Deber M. Javier, recently turned 17, your physics teacher for the duration of this video. In this video, I'll teach you some of the ideas and concepts that lie under electrostatics. Electrostatics is the study of all phenomena associated with charged bodies at rest. Let's begin with a bit of history on the origin of electricity that will further relate us to electrostatics. The idea of electricity began when men wondered about the strange ability of amber and lodestone to attract other materials. Today, we know lodestone as a magnetized iron ore. The earlier men before Christ, particularly the Greeks, have known that amber could attract nearby objects after being rubbed vigorously against cloth. Near to our time, at around the year 1600, William Gilbert found out that many other objects can do the same thing that amber can. He called these objects electrics, from the Greek word electron, meaning amber. But presently we know that all objects acquire this ability to attract small pieces of matter after rubbing against another object. We know that these objects are electrified or acquire charge. Since the charge is at rest, it is often referred to as static electricity. As you may already know, static means unmoving or at rest. Static electricity has always been a part of our daily lives. You can feel a very mild electric shock when you reach for a metallic object after walking across a carpet barefooted. There's also the fly-away hair effect after combing your hair enough times. Now that we're done with a bit of history, let's tackle some of the important constants and formulas in electrostatics. The unit of charge, the coulomb, denoted with a C, is named so in honor of Charles Augustin de Coulomb. The charge of electrons is a constant negative 1.6 times 10 raised to the negative 19. The charge of protons is the same number, only positive, and is 1.6 times 10 raised to the negative 19. The noticeable difference is that in electrons, the constant is negative, and in protons it is positive. If the result of the operation, this operation, is positive, you gain electrons. And if the result is negative, you lose electrons. The charge of electrons is always constant, and it is negative 1.6 times 10 raised to the negative 19. How do we know if an object is electrically neutral? We know that it is so when there is no electron flow, when there is no contact, when the number of protons and electrons are equal, and when the object is electrically charged when the atom loses or gains electron. The protons cannot move because it is inside the nucleus. The electrons, however, can move freely because it is in their nature to move around the nucleus. Static electricity is a buildup of electric charge on the surface of objects. One natural phenomenon of static electricity is lightning, a discharge of static electricity. In a conductor, for example water, metals, and the like, there is a large number of free electrons. In an insulator, for example rubber, paper, foam, and glass, electrons are bound to the atom. Superconductors are conductors that conduct better than gold and practically have no resistance. Semiconductors, on the other hand, like silicon, are conductors that act like insulators. An additional fact: when you are electrically charged and make contact with neutral objects, you will be either attracted or repelled. The electric force between charged particles is proportional to the quantity of each of the charges and inversely proportional to the square of the distance between them. This statement is the Coulomb's law. In equation form, it is this. It is quite similar to Newton's universal law of gravitation. But to differentiate, in Coulomb's law, positive and positive repel, negative and negative repel, positive and negative attracts, and the result can be either positive or negative. Meanwhile, in Newton's universal law of gravitation, positive and positive attract, negative and negative attract, positive and negative attract, and the result is always positive. Some people ask, what kind of force is electrical force? The answer is that it is both attractive and repulsive, unlike gravitational force. In electrical force, F, the K is the Coulomb's constant, which is 9 times 10 raised to 9. Q1 and Q2 denote the charges, and they can be either positive or negative, while the R represents the distance between the charges. Sometimes, human hands need the assistance of machinery and devices. Here are two of the most used devices in electrostatics. First is the Van de Graaff generator. It is an electrostatic generator which uses a moving belt to accumulate very high voltages on a hollow metal globe on the top of the stand. Second is the electroscope, which is used to determine if an object is charged positively or negatively. But how does it work? To know if the object is either positive or negative, you use either a positive electroscope or a negative electroscope. In a positive electroscope, if the leaves diverge further, the object is positive. But if the leaves collapse, the object is negative. In a negative electroscope, if the leaves collapse, the object is positive. And if the leaves diverge, the object is negative. Here are different sources of electricity. Hydroelectric power plants, nuclear power plants, coal and oil-fired power plants, natural gas-fired power plants, geothermal power plants, solar power plants, tidal power plants, windmills, and a natural source for electricity, lightning. Processes of charging include conduction and induction. In conduction, charging is made by contact between the neutral body and the charging body. For example, a neutral body A is brought in contact with a highly negative charged body B. Some electrons from B will go to A. If the two bodies are separated, A gains electrons and becomes negatively charged. B, being highly negative, remains negatively charged. In induction, charging does not involve contact between the neutral body and the charging body, unlike conduction. Let us now discuss the electric field. The electric field lines of force. The conventional direction of charges is always from positive to negative. If there is only one positive charge, all directions go outward. If there is only one negative charge, all directions go inward. If there is a positive and a negative charge, charges move from positive to negative. If both charges are positive, there is repulsion, but in the same outward direction. If there are two charges and both are negative, there is always repulsion, but in the same inward direction. The equation for the electric field is E equals F over QT, where E is the electric field, F is the electrical force experienced by the particle, QT is the charge of the particle in the electrical field. Let us conclude by answering frequently asked questions about electrostatics. First, explain how a charged plastic cone can attract neutral pieces of paper. Does this contradict Coulomb's law? Why is it difficult to demonstrate on a humid day? The answer is, when you bring a charged plastic cone to the pieces of paper, the charge opposite to that of the plastic cone will be brought to a part of the surface of the paper where the plastic comb is. Because opposite charges attract, the pieces of paper will be attracted to the comb. This scenario does not contradict Coulomb's law. This is difficult to demonstrate on a humid day because everything will be coated in a thin film of water, which makes the transfer of electrons more difficult. The water molecules in the film and in the air capture electrons that would otherwise go to the object you are charging. Second, explain the so-called flyaway hair effect of electrostatics. Well, this happens when electrons go flying into your body. When these electrons have nowhere to go, they try to escape, and the last thing sticking out of our body is, of course, the hair. And that's where they go to. Once there's no more static electricity, hair goes back to normal. Third, explain why you get a mild electric shock when you touch a metal object after walking across a carpet. Walking across the carpet will get you charged with static electricity, since it is an insulator. There will be no discharge until you touch the said metal object. Fourth, when a body becomes charged, does it lose or gain weight? Well, the answer is that it will gain the mass of the number of electrons it has gained in becoming negatively charged. But that weight is so minuscule that it will be unnoticeable. 5. What will happen if during induction the ground connection was removed first before the charging body? Well, the charges won't be produced in the body due to lack of object or ground for the opposite charge to flow. And that concludes our FAQ section and the whole tutorial. I hope you have learned a lot from this tutorial. Thank you and good day.